Good morning, students. Let's continue this chapter, system of particle and rotational motion. Now we are done with the center of mass thing. Okay, and now we will look at the different aspect of the rotational motion, and it looks a little complicated, but there's a trick to it that I think there's a trick that you should be applying it and you should be using it, because this makes the rotational motion pretty easy to understand, because based on the previous knowledge that you have. What knowledge you have of the translational motion? So we will relate rotational motion with translational motion, and because you have grasped the concept of translational motion, the terms you have grasped, you will relate what is the similarity in that and this. Okay, and then it will be pretty easy to understand. So I'll take you to the back of this chapter where the comparison is given, that will give us a better idea or better understanding or easy understanding of this terms. Okay, just wait for a second, and there is a last, I think last it is given, otherwise I will just compare without the chart. I think there's a chart is given at the end. Okay, and just a second. Yes, this is the thing I was talking about, the comparison of translation and rotational motion. So linear motion we have displacement, and rotational motion we have angular displacement. Displacement is represented by x, and when you see angular displacement theta, you will see what this is. What was displacement in the linear motion? So it is the rotation, how much angle is when a body rotates, how much angle it move, that is the angular displacement. Okay, velocity, there is a linear velocity v is equal to dx by dt. In rotational motion, this is omega, angular velocity, how fast the angle is changing, d theta by dt. Then we have acceleration is equal to dv by dt, and we have here angular acceleration alpha. This is how fast this angular velocity is changing with time, obviously. Mass, we have mass here, very important term. A lot of discussion has to be go in this moment of inertia I. It plays the same role as the mass. Okay, inertia of moment of inertia. Okay, so whenever we talk about rotation, there is a term called rotational moment of that term. So what role inertia is related to linear motion? Mass increases, inertia increases. Here moment of inertia I. Okay, there are different formulas. General formula is mr square for a point mass at r distance from the pivot point, but there are different formulas, different bodies. There is force is equal to ma. This is the second law. Here force role will be played by the torque, that is the moment of force. Okay, so you must get an idea what I'm trying to tell you, that how to relate this to rotational motion. Tau is equal to I alpha. Okay, so torque is I alpha, force is equal to mass. So what role is playing here? I, moment of inertia. I already told you. Angular acceleration is role is played by, or it is analogous to angular acceleration. Similarly, for work done, small work done, FDS. So force will be played by torque, and displacement will be what? Small displacement ds. This will be d theta, angular displacement. Kinetic energy half mv square. Here it will be half. In place of mass there will be I. In moment of inertia, in place of v it will be omega. Power is 4 times velocity. Okay, here power, force, in place of force will be tau, torque. Okay, I told you torque in detail, and v is omega. Linear momentum, p is mass times velocity. Here will be angular momentum, moment of linear momentum. Okay, I omega. So this is the comparison. Always whenever you get confused in this chapter any term, just open this page and just compare what was this property or this term in translation motion, which property this is analogous to, or which term it is analogous to. You will get a guidance, or will easily you will understand this. So in the next part we will go through all this sum in detail.